Welcome to Networking Concepts section. In this section, we'll become familiar with some of the basic network services that we're going to use throughout this module. We'll look at some of the common network ports that we're going to encounter. We'll look at the load balancer concept, how load balancers work. We'll become familiar with the secure protocols. And finally, we'll talk about the DNS concepts. In this section, we'll get familiar with the basic network services. We'll talk about some of the common network ports that we encounter in this class. And we'll look at the load balancer concepts. We'll become familiar with the secure protocols, the HTTP, HTTPS, SSL, SSH services that we'll talk about. We'll look at DNS concepts. Then we'll finally look at how to scale our applications using AWS. This is a sample network diagram that we might see in a corporation. On the left hand side is we have an internet connection which gets typically connected to a router. In this diagram we are using Cisco router, and we see two firewalls here. This firewall number 1 and firewall number 2. The firewall number 1 has a connection or has a segment of the network typically it's called a DMZ or an extranet. DMZ stands for demilitarized zone, and the internal network or corporate assets are placed behind the second firewall, the second Cisco ASA 5585X router. And this is where we have our database servers, our application servers, and so on. And all these servers are hooked together or connected together with a switch. In this case, we are using a Linksys SR2016 switch. We also see the labels S7, S3, S4, S1 through S10, and these are called communication path or segments. And the network teams or network architects design the networks so that they have rules to protect each of these segments. So every segment or every communication path has to be protected. We need to have certain rules for each of these segments. So this is how a typical network diagram would look like in a company. Next we'll look at some of the different types of connecting these services, these servers that we talked in the previous slide. The first one is a local area network or LAN, which is typically designed for small applications, and all the networks or all the nodes in this network are in a trusted zone. Like I said, it's typically for a small company, small enterprise, or even a home network is also a LAN network. MAN, on the other hand, or a metropolitan area network, is typically designed for a company that has several buildings or a university campus. The wide area network or WAN, on the other hand, covers a large geographic region, and internet is an example of a wide area network or a WAN. About some of the networking concepts that are critical for us to design our systems. The first concept we want to talk about is the bandwidth and latency. A lot of people get confused between those two concepts, so let me take a minute to explain the difference. If you think internet is a series of pipes, the bandwidth is the width of the pipe, how big or how fat your pipe is, and the latency is the length of the pipe. And the latency is determined by the distance between point A and point B and some of the characteristics of that network. In other words, your traffic might be going through multiple hops, like different routers, different switches, different providers. So if you want to transfer a file from the server to client, it might be going through multiple hops, and that determines the latency of your network, and that cannot be changed no matter how big your pipe gets. On the other hand, if you get a better bandwidth or better connection speed, all that means is your server is able to send a lot of data in parallel. So the bigger the pipe, the more parallel the connection speed, the more data can be sent parallelly. So your connection, the total download time may be reduced because you're stuffing more data in parallel. The next feature we want to talk about network concept is the compression. So to enable even faster download speeds, your server might compress the data before sending it to the client, and the client decompresses the data. So your server is sending less data when it to send to the client. The next concept we want to talk about is compression. So to reduce the download time even further, the server might compress the data before shipping it to the client. So in that case, there's some CPU overhead on the server and on the client when it has to decompress the data. But however, your bandwidth usage is less and your download time is reduced. The last concept we want to talk about before we leave this page is the encryption. So most communication that in the modern times, they want to encrypt this tunnel or this channel, communication channel that goes between the client and server, and we use protocols like SSL or services like SSH to establish a secure channel or secure communication between the client and server. So in case there is a malicious user or a hacker that's trying to watch this traffic going back and forth, he won't be able to understand what's going on, because the client and the server have agreed to encrypt this channel or this channel of communication. And when you talk about encryption, we're talking about encryption during transit, when the data moves between the server and the client, and also the encryption at rest. So that means when the data eventually reaches the server and it sits on a disk, we want to make sure the data gets encrypted over there. So there are two types of encryption that we have to work with: data in transit and data at rest. So encryption has to address both these concerns. When you talk about load balancer briefly in the previous section, but the load balancers are designed to front multiple nodes of your application. And if the load balancers are constantly monitoring the health of your instances, and if they detect that the node has failed, it will stop or block traffic to them. They are not only measuring the health of your instance, they're also measuring the response time, how quickly your instances are responding, and then based on that, they might make decision to route traffic to them or not route traffic to them. The load balancers are the core components of a HA system or high availability systems, and every HA systems that we design, especially in cloud or modern systems, uses some sort of load balancers. The load balancers can be hardware or software based. So the load balancer that we're going to talk in the next section, ELB or Elastic Load Balancer, that is a software based load balancer. And the load balancer supports several algorithms in general. The most common one they support is round robin. They might support a random distributions. They might support least traffic. They might identify a server or an instance that has the least amount of traffic and send the next traffic to that. They might detect which instance has the least latency, or to which instance it can get to quickly, and then it might send the traffic to that instance. Or it might be following a sticky session algorithm. In that case, the same client gets sent to the same server all the time, as long as the transaction is continuing for a certain duration of time. Or it might find a server that has the least amount of connections or least number of requests and send the traffic to that. So these are all different algorithms supported by load balancers. And most load balancers support HTTP, HTTPS traffic, and they might choose some TCP ports that we'll see some of the details in the next section. So how do load balancers work? They typically get all the traffic. That's the entry point of your application, and then they distribute the traffic to each server one at a time if they are using the algorithms we talked about. So if they are using round robin, the first user might be sent to server number 1, the second user might be sent to server number 2, and so on. So in this case, we have three servers on the bottom, and each of them will get approximately 1/3 of the traffic if we are using round robin algorithm. The load balancers are typically deployed for web services at the web layer. They might be also deployed at the application layer. Okay. So they might be deployed some sort of load balancer at the database layer also. So load balancers can be deployed at multiple layers depending on the use case, depending on the application. Some of the core concepts that we had to know when we're designing cloud solutions or cloud solutions are network switches, the difference between a switch and a router. So the switches typically connect a small number of devices. Okay. There's a gray line between switches and routers generally, but generally switches operate at the LAN level or the local area network, and the routers are used to send traffic from one network to another. Okay. And in addition to that, routers also find the best path to get data from point A to point B. So the routers are constantly monitoring the optimal path from point A to point B, and they're updating what is called routing rules or routing tables, and they keep the data current all the time. So they might be able to get the data from point A to point B using the most optimal path. The next concept we want to talk about is NAT, or network address translation. So this is a device that's used to hide an entire IP range from the internet. So for the outside network, it might appear that all the traffic is coming from a single IP address. And then in the back end, we might be using multiple devices, multiple ranges of IP addresses on the back end. Okay. So network address translations help us hide that complexity of our internal network from the internet. Okay. And the other benefit is we just need a single IP address now from our ISP, and we could use multiple devices or multiple IPs on the back end. The default gateway knows the next hop. It knows how to get packet outside the internet typically. So all the devices will be configured with a default gateway or a default router that knows how to get packet to the next hop. So when you're on your laptop, you will have at least two routing rules. One rule says if you want to talk within the network, you don't need to talk to the default gateway, the net traffic can stay within. But if you want to go outside to the internet, or if you want to go talk to another network, then you send the traffic to this IP address or this gateway, and that knows how to send the packets to other networks. So these are some of the concepts that we'll deal with when you're designing services in cloud. The next thing we want to talk about is the private IP range, or sometimes you might see references for RFC addresses. And there are three ranges of IP addresses that we commonly deal with: Class A addresses, Class B addresses, and Class C addresses. And the range for Class A is the entire 10 range, 10 network as they're called, from 10.0.0.0 to 10.255.255.255. The Class B address range are 172.16.0.0 to 172.31.255.255. And the Class C range are 192.168.0.0 to 198.168.255.255. So when you say private IP addresses, these are the IP addresses that we can use in our own network. Everybody can use this network. They are free. You don't need to ask an ISP. And typically you will put a NAT device that we talked earlier in front of these private IP addresses. So you might have seen your home network. You have a network at home, and this typically has this Class C range, 198.168.0.0 or typically 1.0. So these are called private IP addresses or RFC addresses that anybody can use. If you look at some of these large networks like Class A and Class B, there can be thousands of machines, thousands of servers that could be created in this network. Most networks are not that large, and typically what network architects or network administrators do is they use something called a subnetting technique or subnetting practice, where they might take a large network and break it into multiple smaller networks. and that improves the IP address usage. It increases the routing efficiencies, and you can delegate administration of those smaller networks to local architects or administrators. So that's what we call logical separation of duties. So the subnetting essentially makes our networking much more efficient. Some of the protocols that we deal with in this course are HTTP and HTTPS. Of course, everybody knows HTTP protocol. We all use it to transfer data from the web server to web browser. The web servers typically run on port 80. They can change it, but this is the default or assigned port number for HTTP protocol. The HTTPS, on the other hand, is the secure version of HTTP. So the entire communication channel between the client and the server is encrypted. Okay. The server in this case, in HTTPS case, runs on port 443. There's an additional step we need to do when we are setting up HTTPS, is that that step is to purchase a SSL certificate and then install on our server or servers. If we have multiple servers, we have to install them on different servers, all the servers, obviously. So when you install SSL, the clients trust your network, and these are typically required for e-commerce sites or banking applications, like we all know. But there is a way to get around installing SSL certificate on every single server. We'll see when we talk about ELB in the next section. The next service we want to talk about for networking is SSH, or Secure Shell service. This is a way for us to log into our EC2 servers or any kind of servers that is typically running that runs a Unix-like operating system, but it doesn't have to be Unix-like operating system. The entire promise of Secure Shell is it encrypts the communication channel between your SSH client that you are using on your laptop and the SSH server. So in the previous labs, we used the SSH protocol to talk using the PuTTY client to talk to the SSH server. So, and the server runs on port 22, so we had to open our security groups so that we can connect to our EC2 to connect to our EC2 servers. Some of the popular SSH clients are PuTTY on Windows, and then if you're using a Unix-like operating system like a Mac or Linux, there are OpenSSH clients that are already built in to your operating system. We could use that. If you want to just copy the files, you don't want to log in, you just want to copy the files from your laptop to the server, or from server A to server B, we use these protocols called SFTP or SCP. SFTP is a secure file transfer protocol, and SCP is secure copy. They both work very similarly, but there's a small difference in the way they implemented it. But the idea is to copy the file securely from one place to another. Some of the popular SFTP clients are WinSCP, FileZilla, and PSCP, which is part of that PuTTY program that we used in the previous lab. Let's talk about DNS, or domain name system. Okay. DNS is the sort of a phone book. It essentially translates the host names that we use when we access any of the services to the IP addresses that the servers or laptops or computers need. Okay. There's a DNS client that gets installed as part of your every operating system, and that DNS client queries the DNS servers for information. So if you are looking for, let's say, google.com, this DNS client or the resolver might query a DNS server and ask for the IP address of google.com. Some of the top level domains that we are familiar with are .com, .net, .org, .info, and there are literally hundreds of them that we might encounter. Okay. But these three are the top TLD domains that we encounter. So how does DNS work? So let's say you are looking to access this site called dnsstuff.com. So you type that address in your browser's window, and immediately it talks to this resolver library we talked about that is part of your operating system. it looks in the local cache to see if that answer is there. That is, if you had gone to that website earlier, that might cache that information in the cache for a few minutes or few hours. If it doesn't find in the cache, then it goes and talks to the DNS server and asks for this information. Essentially, you want to go to dnsstuff.com, but you need that IP address. So the DNS server in that case will send you the IP address, and then your operating system will make that connection to that IP address that we talked about, 63.115.78.98. Okay. And then your browser then establishes that connection to the web server. The web server returns the data that's part of that home page of that website, and then your browser displays that data in your for you. So this is how DNS works at a high level. But if you want to take a deeper dive, in this case you're looking for this website called gohacking.com. Your laptop in this case is asking your local DNS server, hey, I need to know the name or IP address for gohacking.com. So in this case, your DNS server, your local DNS server does not have that answer. So it might ask an authoritative or the owner of the domain for that IP address. So this DNS server might be responsible for answering all the questions regarding gohacking.com. So in that case, the DNS server returns the IP address of www.gohacking.com. Your local DNS server then caches that information and sends back that information to you. Only then your browser is able to establish that connection to gohacking.com. There are several types of DNS resource records or RRs that we deal with. The typical ones are, or the more common ones are the A records or the address records, and that is that phone book that we talked about that translates the host name to an IP address. You might be dealing with C names, which stands for canonical name, or an alias. So in other words, you might have a server, let's say it's called elvis.example.com, but you want, everybody is looking for www.example.com. So because they don't know that you have a server name called Elvis. So typically we create an alias for that, and that in that case we'll say Elvis points to www. So if anybody is looking for sorry, the other way around. If anybody is looking for www, it returns the IP address for Elvis, and then you might get the IP address. You will get the IP address for Elvis server, and then the client establishes that link. So C names are for our own benefit, for our users' convenience, but they are essentially alias records. The next type of record is MX record or mail exchange. So these are the list of email servers that accept email for this domain. So if you have a domain like example.com, so you might have 2 or 4 email servers that handle email for that domain. So this is where you use these records to display or to add your mail exchange records. The NS record stands for the name servers. So these are the authoritative servers for that domain. So these name servers are contacted to get the information about your A records or C name records or MX records. TXT record. It's not very widely used, so you may not see, or you most likely won't see this in practice. The PTR records are the opposite of A records. They translate the IP address to host name. So if somebody says, I have this IP address, I just need to know the host name that corresponds to that IP address, you have to define the PTR records, and then the client will get that the reverse translation in this case. Next, we want to talk about scaling our services. What we want to do is ideally, we want to respond to changes in our environment. We want to make sure that we are adding and removing capacity based on demand. If there is increased demand, we want to increase our capacity. When our users are going down, let's say they go home for the day, or when our site is not busy, we want to reduce our capacity so that we are not consuming compute capacity. We are not using the power and space, right? We also want to meet those capacity that are closely aligned with the real requirements. Well, like we said here earlier, if our usage curve is, goes up in a hockey stick fashion, we want our capacity to keep up with that demand. Okay. And we also want to take out the guesswork of out of the capacity planning. Okay. We'll see some of the challenges in doing traditional capacity planning in the next section, but this is what we want ideally is to automate this capacity planning so we don't make any mistakes which might turn out to be costly. We want to save cost, but at the same time, we want our application to be responsive. We want our application to grow. We want our capacity to grow with our application. So these are some of the services that AWS provides can help you with this automated capacity planning that we'll see. So this is our ideal usage scenario. If our users are, let's say this is 9 a.m. in the morning, and our usage kind of peaks and then falls off at the end of the day, right? And we want to keep on adding servers as our number of users keep going up, and it peaks, let's say around between 3 and 5 p.m. That's when we are running with 15 servers at this time. Okay. As the traffic starts winding down, we are reducing the number of servers. We were at 15 here, and then we go to 12, and then as it keeps going down at the end of the day, we are reducing the servers, go from 12 to 9, and then from 9 to 6, and then finally, let's say this is 9 p.m., we are running only with 3 servers, and this is from 9 p.m. to 9 a.m. we are just running with the bare minimum capacity of 3 servers. So this is our ideal capacity planning curve. So in this section, we talked about networking concepts. We looked at a lot of the services like HTTP, HTTPS, SFTP, SCP. We looked at DNS basics. We looked at load balancer basics. We looked at some of the RFC addresses. We looked at some of the ports that we're going to talk about in the coming sections. We looked at the scaling services. We talked briefly about auto scaling. We'll do a deep dive in the next section. We talked about automated capacity planning when we are designing the services.